Okay, in today's lesson, we are going to cover what we call tree diagrams. Tree diagrams are just another way to represent possible outcomes. They contain the probabilities, and we'll talk about how they kind of help us find those joint probabilities and consider all possible outcomes. So first of all, just nailing down the definition of something actually we talked about in a previous video, but the fundamental counting principle. When we're looking for possible outcomes, the fundamental counting principle helps us to count those without having to list them all. So we'll see that tree diagrams are really helpful if the possible outcomes are, once again, kind of a smaller ordeal. If it gets too big, then actually illustrating those on a tree diagram gets a little crazy. But let's just kind of review the fundamental counting principle. So by definition, if there are n outcomes for one event, right, and m outcomes for another event, then the total number of outcomes for these two events occurring together, so this is the and, is the product of m and n. So we talked about you can look at each event and then multiply their outcomes. So for example, it says the local ice cream shop features ice cream in 24 different flavors. You can order a regular, a sugar, or a waffle cone. Suppose you want to order a double cone, so one with 2 scoops of ice cream. So if we're looking for options, we could look at how many choices of cone, first of all, that you have. And they said there's regular, sugar, or waffle. So there's 3 different types of cones. Flavors for the first scoop of ice cream. It looks like you could choose from the 24 flavors. And then nothing says you can't put those flavors together. So how many do you have to choose from for the second scoop? Also 24. So if we were using the fundamental counting principle to determine how many different double cones are possible, again, we just look at the options. We choose a cone, we choose a scoop of ice cream, and we choose a scoop of ice cream. So if we go ahead and multiply that, there would be 1,728 different combinations of cones that you could create. Okay. So, for example, if I'm going to create a business plan and I decide to open an ice cream shop and offer only 2 types of cones, so instead of 3, we're only going to offer 2, how many flavors of ice cream would you need to offer to have at least the same number of possibilities, right? So if we want to compete with the one across the street. Now, you can do this a couple different ways. A lot of my students will just guess and check. But if you think about it, using that fundamental counting principle, again, you would have 2 there because there's 2 types of cones. And then you would have however many flavors of ice cream, and however many flavors of ice cream, that would be the same value, and it needs to be at least, so greater than or equal to the 1,728. So again, guessing and checking, or we can just go ahead and solve this. So that's the same thing as 2x squared is greater than or equal to 1728. So if I'm solving that, I divide by 2. I end up with 864. And if you square root those sides, you're going to get a decimal, right? So x is greater than or equal to about 29.39 something. So we know that we need to offer at least 30 flavors of ice cream. Okay, so the fundamental counting principle can help us in that way as we're setting up. It's just the product of the possible outcomes of each individual event. So let's look at it one more example. Nathan has 4 colors of polos that he can wear to school and 3 colors of pants in his drawer. So once again, he's got 4 colors for tops, 3 colors for pants. He reaches into his closet to grab a shirt, reaches into the drawer to grab pants. How many different possible outfits? So if he's got 4 colors, and we times it by the 3 possible pants, that would be 12 different outfits. Now it says if he then reaches under his bed to grab one of his 6 pairs of shoes, how many more outfits could he wear? Well, if we take that 12 outfits, right, and then we combine it with shoes, we're going to end up with 72 outfits. So changes things, right? Okay, so that's the fundamental counting principle. Let's talk about how to organize outcomes on a tree diagram. Tree diagrams are a useful method of illustrating a sample space of outcomes when understanding compound events, so more than one thing happening. Once the sample space is illustrated, then we can talk about the tree diagram and the branches and which ones apply to what we're trying to find. So this is how to create one. Step number 1, you got to identify each event for what it is. So identify the first event, what's happening first, and then create a set of tree branches to represent that outcome. Number 2, you identify the second event. Create a set of tree branches off each of the first event's outcomes, and then you continue this pattern for each event. And then we probably would add a step 4, which we put clear down here. We would add the probabilities. So let's just look at this one. It says, suppose Adeline wishes to dine out in a local restaurant. She looks up the menu online and realizes she has a choice of 3 soups, 2 types of rice dishes, and 2 desserts. Build a tree diagram to represent the possible meal combinations. So she has to make a choice first. It doesn't really matter which one she chooses first, but let's say she chooses the soup first. So when I create the soup, I go ahead and I create 3 branches because she has 3 options: soup number 1, soup number 2, or soup number 3. Each of those are different meals. Then she has 2 possibilities for rice dishes. So if she orders soup 1 going up that top branch, she could get rice 1, or she could get rice 2. Now recognize here's a meal, soup 1, rice 1 so far. That's a different meal than if she gets soup 1, rice 2. So each branch is leading us to a different meal. She could get soup 2 and then rice 1, or soup 2 and rice 2. That's a different meal. Same with this one. So rice 1 and rice 2. And you could see that if there were a lot of outcomes, these trees could get really messy. Then lastly, she's got to pick a dessert. So if she gets soup 1, rice 1, she could get dessert 1 or dessert 2, dessert 1 or dessert 2. And same thing going off of each of this. And I have to draw the lengths, different lengths, so I can fit them all in here. Dessert 1, dessert 2, dessert 1, dessert 2. Now again, recognize that every one of these branches all the way to the end, we're not going to stop in the middle, but all the way to the end would represent one of those meals. So soup 1, rice 1, dessert 1, or soup 3, rice 1, dessert 1, right? Every one of these represents a little bit different of a combination. There's all the soup 2, rice 2, dessert 2. So if I was counting this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there's 12 branches all the way to the end. And again, using that fundamental counting principle, we could do 3 times 2 is 6, times 2 is 12. So we know that that represents all the 12 outcomes. Now once we start calculating, we will actually put some probabilities on top of these branches. So I'm going to show you how that looks. But essentially, if we were doing it on this one would be maybe a little bit odd, because maybe she'd prefer one over the other. But the probability, right, that she would choose the first soup would be 1 out of 3 soups, because there's 3 possibilities. Rice 1, she can either choose rice 1, so 1 out of the 2, or rice 2. So notice that all the branches, right, relate to the possible outcomes. And then the dessert would be the same there, because there's 2 desserts, so it would be a 50% chance of which one she chooses if there wasn't a preference. So we could add these probabilities here, and we'll kind of look at some other examples of how we then use that to calculate. Remember the formulas for joint probability here. If we're talking about this happening and this happening, then we just multiplied the outcomes. And then remember, if it's an or this, then we just added together all the probability outcomes. The addition law of probability, if the probability overlaps, and they won't much with your tree diagram, you'll be able to see them individually. This would be an example like the probability, if I'm drawing from a standard deck of cards, that I get a hearts, or, again, that's the or, a red. If you think about that, the probability of getting a hearts, which is the first event, would be 13 of them out of 52 or 13 hearts out of 52 cards, or a red. There's 26 red out of the 52, but you included those red hearts in this one and this one, so it's kind of like you would subtract out what you double counted. So that's essentially what this means when you're doing an or. The tree diagram is going to help us distinguish between those. So let's jump down here and try one of these, and we'll show you what it means. So this example says, draw a tree diagram to illustrate the outcomes of flipping a coin, then rolling a die. So if I'm flipping a coin, that's the first event. There are 2 sides on my coin. It's either heads or tails, so that's my first set of branches. The probability of getting heads would be 1/2. The probability of getting tails, 1/2. Then rolling a die, that would be 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. And again, this is one, maybe I wouldn't use a tree diagram because the probabilities are so simple to actually find, but it's a good one to start with as we're recognizing. So the probability of getting any one of these numbers is 1/6. Notice on that branch that accounts for all 6 out of 6 possibilities. So we want to make sure that we're always making sure those branches add to the 100% or the whole possibilities. So this one down here says use the tree diagram to calculate the probability of flipping ahead and then rolling a 4. So if you look at this, flipping ahead goes down this branch and, right, rolling a 4. So to get to the end of a branch, you multiply the outcomes. So one of them is 1/2 times the 1/6 to get all the way out. That would end up with 1/12. So, and takes us to the end of a branch because this is happening and this is happening. So again, we would do the 1/2 times the 1/6. Oop, that's messy looking. And that would be equal to 1/12, or 8.3%. The next one says use a tree diagram to calculate the probability of flipping a tail and rolling an odd. So probability of tail and an odd. So again, you would look at this and you would say, okay, going down this one, here's a tail, and this goes out to an odd. So that would be 1/2 times 1/6. Or there's other branches, so it could come out a tail and then get a 3. So 1/2 times 1/6 takes us to the end of that one. Or, and every time we say or, again, we add another branch. We could do tails and then roll a 5. That's still an odd. So there's another 1/2 times 1/6. So these ones all have the same outcomes on each branch. So if we just take that and add that all together, we get 3/12, or in other words, 1/4, 0.25, or 25%. Okay, let's look at another example. So each day, Carl looks out his window to observe the weather and makes a decision on whether he will ride his bike or ride the bus to work. So think about the decisions or the events as we go. So bike or bus. If it's raining, Carl's going to wait for the bus. So rain, he's going to wait. If there's no rain, then he'll ride his bike. When Carl rides the bus, the probability he'll be late for work is 0.63. When Carl rides his bike, the probability he's on time to work is 0.8. The weather report shows that tomorrow the probability it will rain is 40%. Draw a tree diagram to represent the situation. So again, the first thing we have to do is say, well, what happens first? He's going to choose to ride his bike or the bus, right? And it depends on whether it rains or not. So what we're going to do is we're going to say, okay, let's use the actual writing thing. So bus, and he's going to ride the bus if it rains. So I'm going to write them both so we recognize that's what it stands for. Or he's going to ride this bike, and he'll ride his bike if there's no rain. Okay. Again, when he rides his bus, when he rides the bus, he's either on time for work or he comes in late. Same thing, right? On time or he comes in late. So again, it said that when he rides the bus, the probability that he'll be late is 0.63. So we're going to put 0.63 now. Now, if the probability he's late is 0.63, then on time is the rest of the time for this event. So again, remember, we just do 1 or 100% minus the 0.63. And so the rest of the time would mean 0.37 or 37%. So we want to put that on there. It then tells us that when he rides his bike, the probability he's on time is 0.8. So this one tells us when we go down the bike lane and he rides his bike, he's on time 0.8, or 80% of the time, which makes him late 0.2% of the time. Once we have our tree diagram, we can answer the question. So what's the probability it will not rain tomorrow? Oh, I forgot to add those probabilities. So it told us that the probability it's going to rain is 40%. So rain would be 40%. So again, if it rains 0.4 or 40% of the time, then it's going to not rain 60% of the time. Those have to add to 100% or to 1. So not rain tomorrow, looks like it's going to be 60% or 0.6. Okay. The next one, what is the probability Carl will ride his bike to work tomorrow? Notice that's the same thing, right? Those ones just represent the same thing in our tree diagram. So it's not raining means he rides his bike. What's the probability Carl will be late to work? Now here's the tricky one, is sometimes we see, oh, late to work, we go to our tree and we just say 0.63. Or we add it to the 0.2 and we think that these two relate. But remember, the probability that he rides his bike affects whether he's late or on time. So we need to look at both of those. So when we look at this, we say, okay, well, either he rides the bus and is late, so that's one option. So again, we go 0.4 times 0.63 to get to the end of that branch, or means plus, he rides his bike and he's late. So we have to add all the branches that apply to him being late to work. And then we just multiply that. So we end up with 0.372, or in other words, 37.2%, however you'd like to write it. Okay, so again, the probability of being late, just recognize there's more than one branch that takes you there, right? It's either the bus and then he's late, or, and every time it's or we add, it's the bike and he's late. So we have